Hello, welcome. This is the AQA AS Physics. This is the AS Unit 1 January 2009. Quite smooth. Okay, this is obviously question number 4. Quite a short question, only worth 8 marks. Okay, there's no real diagrams involved. Anyway, let's kick off. So 4A says, state what is meant by the wave-particle duality of electrons. Okay, now whenever you hear wave-particle duality of anything, is the fact that it has a particle and a wave like nature. Okay, so it's not asking for you to give examples of how electrons are like waves and are like particles, although that'll probably come on in some kind of another question. But anyway, just simply state, it might as well be asking what is meant by wave-particle duality, but you just reference it to being electrons. Okay, so it's when electrons have a wave-like nature and a particle-like nature. Okay, that's all you need to say for 4A. Okay, 4B says electrons have a wavelength of 1.2 times 10 to the minus 10 meters are required to investigate the spacing between atoms in a crystal. Calculate the momentum of an electron of this wavelength, stating the appropriate unit. Now, for those of you that are thinking, what the hell is it asking about momentum, or how are we going to relate momentum to this, is probably the better way of saying it, you more intelligent people. Obviously, momentum is mass times velocity, but it says wavelength, okay? So, as with all physics, you write down what the wavelength is. What you're given in the question. So, we're told that the wavelength is equal to 1.2 times 10 to the minus 10 meters. Okay. And obviously we know the mass and charge of an electron, but we're not going to write that down until we can kind of spot a pattern here. The momentum. Well, the only thing that relates this wavelength, the fact that it's told us a wavelength, is obviously the biggest key to answering this question. Okay. Now, wavelength. The only thing that we see wavelength in when we it's just mentioned wave-particle duality, so that should kind of give you a bit of a heads up. We're going to be using the equation lambda is equal to h over mv. And as I said, mv is momentum, so lambda is equal to the Planck's constant over momentum. Okay, and it's asking for the momentum of the electron of this wavelength, stating an appropriate unit. So we've got the wavelength, obviously you know what Planck's constant is, which is 6.63 times 10 to the minus 34, okay, and we know the mass of an electron, so we might as well note that down as well. So the mass of the electron which is 9.11 times 10 to the minus 31. Okay, so it's in kilograms. Okay, so lambda is equal to h over mv, so you just put it equal, so 1.2 times 10 to the minus 10 meters is equal to Planck's constant, 6.63 times 10 to the minus 34. In that case, you might as well note down what Planck's constant is as well, it's up to you, over the momentum. Now, it's not asked us to, actually, I've told you, I've noted down the mass of the electron, but it doesn't matter, because it's not asking us for the velocity, it's simply asking us for the momentum. Okay, but that will come in handy in our next question. Okay, so, just a case of rearranging this, so if you times both sides by the momentum and divide both sides by the wavelength, okay, you'll get the momentum equal to 6.63 times 10 to the minus 34 over 1.2 times 10 to the minus 10 meters. Okay, so let's say just whack that in your calculator and you should get an answer of 5.5 times 10 to the minus 24 meters. Sorry, times 10 to the minus 20, minus 24 kilogram meters per second. Yeah, so state an appropriate unit, so any unit would do for momentum, but you have to remember that the you could just look at the units for Planck's constant and divide and do that m to the minus 1, or you could simply do, well, I know momentum is kilogram meters per second, so I'll shove that in there. Okay, it's up to you. Right, well, 4b part 2 kind of goes off what I was saying here. I've noted down what the mass of the electron is. I probably shouldn't have done that until the second part. It's asked us to calculate the speed of such an electron. So we don't need to do all this calculation again because we've already done it. And, well, you could, and it depends how much of your life you actually want to waste. Okay, so we know momentum is mass times velocity. Okay, so yeah, so we know the mass of the electron, we know the velocity it's going at. Now, I personally, this 5.5 times 10 to the minus 24, it's up to you how accurate you want to be with this. But personally, what I like to do is basically use this exact, obviously when you type that, and when you type your calculations, get the answer for B part 1, your calculator will give you the most exact answer you can get, okay? Because obviously you can't do it in your head. So I would use that exact answer in your expected calculation. Okay, so I'd keep that saved in your calculator and just write this down with the numbers still in your calculator. Okay, so we know the momentum is equal to mass times velocity. So that's the first thing I would state here. Momentum is equal to mass times the velocity. Okay, and we know the mass and we know the velocity. Sorry, we know the momentum and we know the mass. So you could just rearrange it straight off the bat without subbing in numbers in just yet. You could sub in numbers if you wanted to, but this is a very easy calculation to rearrange. So I don't think there's any need to sub your numbers in at this point, and then rearrange it. Personally, I would rearrange this equation, momentum equals mass times velocity, and then sub your numbers in. But for more complicated equations, the ones that, square root and whatever, I would personally sub your numbers in, then rearrange. But just to make it that more confusing, I'm going to rearrange it, then sub the numbers in. Okay, so we want velocity, so velocity, therefore, rearrange this equation is equal to momentum over mass. Well, we've just worked out the momentum in B part 1, which was this 5.5 times 10 to the minus 24 kilogram meter per second. But as I say, I would just sub that in as your answer, copy it over from your answer calculator stored memory over the mass, which is the mass of an electron, 9.11 times 10 to the minus 31 kilograms. Okay, obviously the kilograms cancel and you get your answer in meters per second. Okay, which gets you 6.1 times 10 to the 6 meters per second. Okay, so that's crucial, by the way. We're going to be using that in the next little bit. 4b part 3 says calculate the kinetic energy of such an electron. Okay, so we know that the kinetic energy equation is half of mv squared. Now what I'm going to do now is just kind of sort all that out, and then I can do it a bit neater if that be the case. Okay, so in this bit we're meant to calculate the kinetic energy of the electron. Now, as mentioned, the kinetic energy is equal to a half of mv squared. Okay, we've just calculated the velocity of the electron. Okay, trying to think of what it was called then. Okay, and the velocity of the electron was, so you think I would remember this, God's sake, 6.1 times 10 to the 6 meters per second. Okay, and obviously we know the mass of the electron, 9.11 times 10 to the minus 31 kilograms. Okay, so just sub their numbers into the kinetic energy equation. Okay, it's very, very simple, 2 marks, half times 9.11 times 10 to the minus 31 times the v squared, 6.1 times 10 to the 6. So therefore, as I just whack the numbers into the calculator, you get 1.69 times 10 to the minus 19 joules. Sorry, minus 17 joules. As you can tell, I've obviously already done these questions. Okay, so that's your answer to question 4. Hopefully it's been helpful, and again, it's quite a short question, only worth 8 marks, so any questions you might have, please let me know, and try to answer them as a human being. But really, that's the end for this video. Thanks for watching, and we'll see you in the next video.